So, hi, I'm Ryan. I'm an applied machine learning intern as well on the AI engineering team. And today I'll be talking about my work this summer into understanding the current status of vertical federated learning research and tools. So this is part of an effort that Sarah, Sophie, and Shems and I did on the PETS project. So I included this figure here. This is some of the privacy enhancement technologies that our group has looked at, and Sarah has mentioned some of them, and I include it for the purpose to remind you that vertical federated learning is a particular flavor of a particular technique of privacy enhancement. And it's distinguished in that it's focused particularly on specific practical applications. And because of this, we have heard lots of excitement about vertical federated learning from our partners. And as Sarah said, in practice, a lot of multiple of these techniques are deployed in conjunction to ensure privacy and security. So their use cases are not entirely distinct. Yes, a common problem arises in the friction between data-hungry models and privacy regulation. And Sarah described this problem and used the example of hospitals. So I'll continue this example as I talk. So just to reiterate, there's a number of hospitals and they want to generate a model that can make some common diagnoses, but they have restrictions on how they can share their data. So federated learning has been proposed as a solution to this problem. And as Sarah said, federated learning is described as a process where devices collaboratively learn a shared prediction model while keeping all of their training data decentralized. And this is the process that is depicted in this diagram. The problem with this vanilla federated learning setup is that it assumes homogeneous data. This actually will be in part to your question as well, Elham. So let's go back to our hospital example. In the real world, not every hospital is identical, collecting identical data and only differing in the population of patients it serves. There are some general hospitals, some specialized hospitals, and they all collect data, different information in different ways. Data in the real world is often heterogeneous like this. And when you're collaborating across databases and institutions, which is often the case in federated learning, this is especially true. And once again, it's not limited to just hospitals. This is true of data generated in other sectors, including banking and retail. So to further demonstrate the distinction between horizontal and vertical federated learning, let's take a look at this diagram. So the difference between these two types is how the data is partitioned. So in a horizontal partition, the client's database holds many different customers, but they're collecting all the same type of data on those customers. And in vertical, you have different customers in both, but there's an overlap of those customers and they're collecting different features. So you can see here the shape is the features and then the color are the people. So you can think of vertical federated learning as multiple organizations that have different data on the same customer. And the complication is that a single person's record is split across multiple databases, unlike the horizontal partition setup. Training deep learning models on vertically partitioned data is called vertical federated learning. And here's how it generally works from a high level perspective. First, users are aligned between the databases. This process securely finds an overlap between the people in each database and returns the intersection set. Then this intersection set is used to train the model by calculating and sharing partial results and passing them around to enable back propagation. The first step, user ID alignment, is usually completed with a technique called private set intersection, which is a secure multi-party computation that allows parties to compute the intersection of sets without revealing either party's individual set. The only thing that's revealed is the intersection. And there's even a technique called private set union that doesn't even reveal this. Often the identifying feature of the samples will be something like phone and email, which is universal across all organizations, unlike the internal database ID, which will be some organization's unique customer identification number. So you can see here in this diagram is an example. There's one company, which is a blog publisher, and then the other company is a bookseller. And you can see they collect different features on each customer, but they have an overlap of person A and person C. There are many different methods of model training, but I'll briefly touch upon two of them, split NN and FedBCD. They both require each party to share intermediate results in order to update model parameters using backpropagation. So the split NN method involves splitting a model into segments, and each party trains individually. And then these split segments output an intermediate representation, which is used as an input for another. And when during training, the gradient is propagated across these segments. And in FedBCD, which is federated block coordinate descent, parameters for each client's model are updated multiple times locally, and the parameters don't need to be shared explicitly in every interaction. So the improvement of FedBCD is that it reduces the communication overhead, which is often a bottleneck. Existing open source tools for vertical federated learning are hard to use. They are research focused, and it really shows. There's little to no documentation, little or no working examples, and they may not be compatible with some of the model codes you already have. The features differ across the libraries, and I've listed some of the important ones here to consider. There's a distinction between libraries that can only run in local simulation or ones that can also work in a real-world distributed computing scenario. It is also to consider what type of vertical federated learning algorithm the framework has, FedBCD, split NN, or maybe even another. This diagram provides an overview of the existing tools and their features. However, in my experience, this chart doesn't tell the full story because the frameworks have varying levels of usability as mentioned previously. Things are changing quite quickly, and as Sarah said, during the internship, some things would be broken and then fixed and then broken again. So these libraries are pretty rough around the edges and not entirely ready to use. However, I want to focus on a particular finding from my evaluation. There is a critical need that has yet to be addressed, and it's limiting VFL research and practical application. And that is, there are very few data sets and no good standardized benchmarks for vertical federated learning. The data sets used to develop and evaluate vertical federated learning frameworks are inconsistent between all the frameworks I explored. And more importantly, they don't reflect the nature of vertically partitioned data that exists in the real world. This is a big problem. Take, for instance, this data set here, which is a version of MNIST, which has arbitrarily been converted into a vertical federated learning data set by splitting the images in half. This is all right for a first step proof of concept, but in order to push the tooling into the real world, it is inadequate. These toy data sets make it hard to compare the frameworks, and they don't give a good benchmark on how it would perform on real world data. A proper vertical federated learning data set and benchmark needs to have a structure that reflects the messiness of this real world vertically partitioned data. And some of the characteristics are listed here. First off, the data set should have partial labels. So this is when only some of the organizations hold the target label. This is often the case in our example hospital setting. So certain lab results can be the label for prediction, but these results may not be allowed to be shared across the organizations, all the organizations where the patient has data. However, this is a major assumption that all the organizations hold a target label of many vertical federated learning frameworks, and one that isn't really true in the real world. Second, the data set should have unbalanced clients. So this is to Elham's point, a lot of times there's one general hospital that has much more data than a laboratory clinic that a patient visits once or twice. And this is a challenge that vertical federated learning frameworks have yet to address because the data sets used for building them don't have this characteristic, which actually does make it much harder to learn. Third, the benchmark should come with example restrictions on data leakage. So oftentimes it's not good to release that intersections that I talked about before, because it might actually be private information itself that this person is a customer of multiple companies or has been to many hospitals. So similar to the partial label problem, it is important to keep these things confidential. Lastly, the data set should be for a relatively complex task, similar to a real world task. And this is because these tasks require more complex or more specific model architecture. So current data sets are very simple and they're not rigorously tested throughout the VFL framework. And these task-specific architectures may require improved VFL algorithms based off of their unique characteristics. In addition to being characteristic of real-world data, the benchmarking data set should be entirely publicly available, which means it can't have any sensitive information, and it should be a task where models and evaluation tools exist. And this is for the purpose of comparison. This way it can properly be compared between VFL frameworks, but also can be compared to non-VFL setups where there's no privacy to really understand the performance losses and gains of these methods. So I think this is a key opportunity for us at Vector. I think that this change needs to happen before VFL tools are mature enough to use in practice. And I see an opportunity for us to work with some of our partners and try to find some suitable data for the goal. The partners also have an incentive to help us out because they see potential value in the practical VFL. I'll leave you with the key takeaways from this presentation. So first, vertical federated learning is really important to a lot of real world use cases and challenges a lot of the assumptions and previously held in federated learning. The frameworks, however, are very much in their early stage development, and we will want to keep an eye on both how the tools and the theory develop. And how do we do that? How do we know when it's time to dip in our toes or take a plunge? Well, you should consider the factors that I described previously. And lastly, there is an immediate need for a benchmarking data set in the vertical federated learning ecosystem. That's it. Thank you for listening to my presentation. If there's any questions, I can hear them now.